Hello everyone, welcome to the lecture for April 6th. Let's just go right into it. Last time we talked about the certain properties of groups, so in general. So we defined a group not too long ago, and we tried to develop some of the theory around groups in general last time. In particular, we discussed the notion of order, and we also discussed sort of how the associativity properties and things like that can be used to talk about powers of elements. And powers of elements is how you determine the order of an element anyway. And at the end we talked about a theorem that told you how to compute the order of an element of the symmetric group Sn. And today we're going to be focused on proving that. So the first theorem we prove on the way to computing the order of a general element is to find the order of a cycle. And this theorem is basically intuitively obvious, and we're going to do a few drawings here first before we actually write down the formal proof. But the idea is very clear. So remember what it means to be a cycle. It means that the moved set consists of elements k1, k2, up to km, and my permutation pi just moves between the two. So pi of ki is equal to ki plus 1. And everything else is fixed by pi. And sort of we had this picture before when we were talking about orders of elements, that you just keep going around a cycle or circle until you get back to where you start. And the key thing to note here is that when I go around m times, then I get k1 gets mapped to itself, k2 gets mapped to itself, and k3 gets mapped to itself, and so on and so forth. So if m is certainly a number such that pi to the m is equal to the identity, because all of these guys get fixed, and these are fixed by pi. So if I keep iterating pi, it's just going to keep fixing them over and over again. So m is an element that fixes everything, and hence equal to the identity permutation, right? We're looking for the number m such that when I raise pi to the m, I get the identity element of the group, which in this case is the identity permutation. So m is one such element, and it has to be the smallest such element, because if you choose any number smaller than m, k1 is taken to something that's not equal to k1. So it's not the identity permutation anymore. So how do we convert this very simple idea into a proof? So notice that for I between 1 and m, pi to the m minus 2 of k sub I is k sub m minus 1, or is k sub m. Sorry, this should be m minus I. Let me make sure I get my indices right here. Well, let's actually prove this by induction, right? And we can check the induction case. We'll prove it first for I equals m. So when I equals m, this is pi to the 0 of km equals km. So let's just prove this subproof by induction, just to get some practice with induction. This is basically clear, but what I'm saying is that when I go I'm trying to find how many steps it takes for me to get up to km. So pi to the 0 of km equals km. So this is the base case. I equals m. And once I have it for I equals m, then once I have it for I want to prove it for a lower number, right? I start with m, and then I'm going to go down to 0. So pi to the m I minus 1 of k sub I minus 1. Well, pi of pi inverse is the identity map. And pi has an inverse. So I can add a pi inverse here. Well, let's just do it slowly. Right, I have an okay, let's do this slowly. So this is one of the exponent rules we proved. And then by definition of a cycle, pi of k sub I is k sub I plus 1. So when I apply pi to this, I get pi to the m minus I of k sub I. And by induction, this is k sub m. So when I have this identity that pi to the m minus I of k sub I is k sub m, which means pi of pi to the m minus I k sub I is back at k sub 1. This is just the definition of pi on k sub m. Now if I apply pi I minus 1 more times, I take I minus 1 more steps. So this is k sub 1 plus I minus 1, so I just get back to k sub I. If I add all these numbers up together, I should get, right, so this is pi to the 1 here. I have my I minus 1 plus m minus I is just pi to the m. So this was a very sort of maybe over-encumbered proof that pi to the m fixes every element of the cycle, and it has to fix every other element, also by induction, right? If pi of a number L is equal to L, then pi squared of L is pi of L. I replace the internal pi of L by L, and then I just get pi of L, which is L. So each time I apply pi, I'm not changing the number. So what this shows is that pi to the m is equal to the identity transformation. So the order of pi is at right, the order is the smallest number such that this happens. So it could be smaller, but it's at most m, where m is the length of my cycle. Should have called it L maybe. On the other hand, I want to claim that it's equal to m. So I want to show that if I choose a number smaller than m, then it doesn't fix everything, right? There's something moved. It's not the identity transformation. But if n is the number of elements I have, so I don't want to use n. I've already used k. I guess I use L here. But if L is less than m, pi to the L as a permutation acting on k1 is k to the 1 plus L. And there's no way that this could be equal to k1, right? Because k1 plus L is smaller than or equal to m, and these are all distinct numbers. I have k1 up through km, all distinct. So since 1 plus L is less than or equal to m, and it's also bigger than 1, at least 1, so L is positive, these numbers are different, and k1 is moved. So therefore, m is the smallest integer such that pi to the m is equal to the identity transformation as a transformation. And so that is, m is the order of pi. Okay. So I wanted to go through this proof a little bit more carefully. It's not even more carefully, because you can have fewer details and still be just as careful in the proof writing. But I wanted to go through this proof sort of in more details to show you just how detailed you can try to be and how powerful induction as a tool is. These things are basically obvious. In most mathematical writing, you'll see people skip these types of arguments because they're fairly standard. But induction can be used to prove things that are intuitively obvious just from definitions that are well made. So the fact that we made our cycle definition using this, and also we have pi of km is equal to k1. So using these definitions, we were able to prove exactly the cycle property. That the order of a cycle is its length. Something intuitively very clear. Okay, so if you remember, one of the things we proved about permutations is that they're always a product of disjoint cycles, which means two cycles are a disjoint, or two permutations in general are disjoint if whenever something is moved by one permutation, it's fixed by the other, and vice versa. So the things that pi is moving and the things that sigma is moving are totally different. So it makes sense to ask what happens when I take disjoint permutations, take their product, so I take their composition, right? The group operation for permutations is composition. So when I take the product of two permutations, what is the order? Well, it's just the product, or the least common multiple of the orders of each of pi and sigma. Okay, so let's prove it. So let S equal the order of pi, and R equal the order of sigma. Then if L is the least common multiple of S and R, L is S times K, and L is S times m for some k and m, r times m for some k and m, which are natural numbers, right? That's just what it means to divide. If you remember last time we talked about the least common multiple, and we said that the least common multiple of two numbers s and r is the smallest number such that both s and r divide it. So because L is the least common multiple, I know that S divides it, so I have this equality for some K. And R also divides it. So I have this equality for some M. Now what happens when I raise pi of sigma to the power L? Well, if you remember, one of the things we proved is that pi and sigma commute, right? So this is just pi sigma, pi sigma, pi sigma L times. So I can rearrange it to be pi to the L, sigma to the L. And this happens only because pi and sigma commute, since they're disjoint. But pi to the L is, well, L is r times m. So this is pi to the r to the m, sigma to the k, to the s to the k. And these are both the identity transformations. So when I compose the identity with itself, no matter how many times I compose it, I end up with the identity. It fixes everything. So this shows that the order of pi of sigma, the order of the composition, actually divides L. And now I want to show that it's actually equal to L. So how do I do this? Well, I want to assume that I have some power of sigma, pi sigma that's equal to the identity. Let's think of another letter name, A. Well, in this part of the computation, I didn't use the fact that L was this least common multiple of S and R. So I can still split this product up, this power of pi sigma up into pi to the A, sigma to the A. But now look at what happens. If K is fixed by sigma, then sigma to the A of K is K, right? Sigma just keeps fixing it over and over again. No matter how many times I apply it, so I apply it 8 times, I get K back. But pi to the A is K. Because the identity of K is equal to K. This is when I apply this to K, I get K, so pi to the A of K is equal to the K. Now what happens if K is not fixed by sigma? Then what happens? Well, I sort of switch the roles, right? If it's not fixed by sigma, then it's moved by sigma. So it has to be fixed by pi. But if it's fixed by pi, then raising pi to the 8th power on k is equal to k. Again. So no matter which type I choose, whether if phi is fixed by k or moved by k, pi to the a of k, if k is fixed by sigma or not. Right, here we looked at the case when k is fixed by sigma, and we got that pi to the a of k is equal to k. And if it's not fixed by sigma, just by definition of disjointness, it must be fixed by pi. So it has to be fixed by pi to the a. So no matter what k I choose, pi to the a fixes it. So in particular, pi to the a is equal to the identity. Now once pi to the a is equal to the identity, I can plug it into this and get the sigma to the a is equal to the identity. Right? Because the identity composed with any transformation just gives me that transformation back. Now what did we prove? We proved that if you take two group elements of any group, and you not two group elements, but one group element. If you take some power that's equal to the identity element of the group, then the order has to divide that element. K divides L, A, and L divides A. And now we just need a basic little lemma. If K divides A and L divides A, sorry, if S and R were the orders of sigma of pi and sigma. So if S and R divide A, then the least common multiple, L, also divides A. And this is a very basic corollary of the unique prime factorization theorem and the expression of the least common multiple as using it. So we didn't prove this before because we never even made the definition, but let's actually prove it quickly. Notice that if S is some product of powers of primes, and so is R, so this is NK, M1, MK, then the least common multiple of S and R is P1 to the, let's just give it a new name, B1, PK to the BK, where BI is the max of MI and NI. Right, so if I took the GCD, I would take the min, right? Because I want the GCD to divide into this. But because I need S and R to divide into both to divide into the least common multiple, I need to take the max of Mi and Ni. And indeed, you can check that with this choice of BIs, any S and R will both divide into the least common multiple. And so on and so forth. That's the smallest one as well, because if I try to lower the BIs anymore, then one of these would fail to divide into it, whichever one was larger. Okay, so I have this least common multiple. And now what's the claim? The claim is that if S divides A and R divides A, then L also divides A. Well, divisibility can be checked just by checking whether or not the exponent of the prime is smaller than the thing you're dividing into. Right, so A here would be also written as a product of primes. Maybe you'd need more primes, but you would certainly you could use these primes, maybe including 0. And if S divides A, then the exponent of A has to be larger than all the Ni's, and it also has to be larger than all the Mi's, since R divides A. Therefore, it has to be larger than the maximum of them, because it has to be larger than both of them. So in particular, the least common multiple of S and R will also divide. And that shows... Okay, so this was a very rough sketch. So I should say this is a sketch of proof of lemma. It's a good exercise to review sort of what we talked about with GCDs. This is sort of a dual to GCDs. So similar, but not exactly the same. So let's recall what the statement of the lemma was and how we got to the end. Let's just take a step back and recall everything. So the lemma says that if you have disjoint permutations, the order of their product is the least common multiples of each of their orders. So how did we prove this? Well, first we showed that the least common multiple is something that that when I raise their product, pi sigma, to this power, I get the identity transformation back. And for this, we heavily use the fact that the permutations were disjoint. If they're not disjoint, this lemma isn't true. So because they're disjoint, they commute, and so I can distribute the exponent onto each of these two terms in the product. So I get pi to the L times sigma to the L. And then using the property of least common multiple, we checked that these powers are both equal to the identity as a transformation. Now, what is the order? This shows that the order is certainly smaller than L, but why is it equal to L? Well, the idea is to show that L, if you have any power of sigma pi that's equal to the identity, it has to be an order of pi, or a period of pi. So the order of pi will have to divide A, and the order of sigma will have to divide A. So the least common multiple is going to be the smallest number, such that K and L divide it. And so we win. So again, we heavily use the fact that they're disjoint. So we use that here as well. Now what do I want to do? I want to show that pi to the A is the identity transformation and sigma to the A is the identity transformation. So how do I show that something is the identity transformation? Well, I just evaluate pi to the A on an arbitrary element and show that it fixes it. And there are two types of elements. There are the elements that are fixed by A and the elements that are not fixed by A. Every K has to either be fixed or not fixed. So if K is fixed by sigma, then of course when I take a power of sigma, I just get that element back. So when I look at this equality, I see that pi to the A of K is equal to K. Now disjointness says that whenever I'm moved by sigma, I have to be fixed by pi. So the things that are not fixed by sigma are moved, and everything that's moved by sigma has to be fixed by pi. So this one is actually the easier case. Once I'm moved by sigma, I know that pi itself already fixes it. So pi to the a certainly also fixes it. So combining these two, every k, whether it's fixed or not, is going to be fixed by pi to the a. So pi to the a is the identity transformation. That's going to tell me that S divides A, right? Because the order has to divide every number, which is for which the power is equal to the identity transformation. And we can similarly prove, either by this argument or just reversing the roles of pi and sigma, that sigma to the a is equal to the identity, which gives me that R divides A. And then I just need this little lemma about least common multiples, that it's we have a similar one for GCDs, right? Except it's reversed, right? If A divides S and A divides R, then A divides the GCD. For least common multiples, it's reversed. If S divides A and R divides A, then the least common multiple divides A. So this means that A has to be at least L, if it's positive. So the order has to be at least L, but it also has to be at most L. Therefore, it's equal to L, and I get this lemma. And now we are ready to prove the main theorem of this section. One of the main theorems, I should say. So what does this theorem say? It says that if you give me a collection of disjoint cycles of given lengths, then the order of this long product is this least common multiple of the lengths of the cycles. Well, how do I prove this theorem? Well, maybe you can guess. It's going to be by induction. So the base case is 2. K equals 2. So if I have 2 disjoint cycles. This is the previous lemma. Plus the fact that the order of each of these cycles is and sigma 2 are L1 and L2, respectively. Right? Because then I have sigma 1 and sigma 2. They're disjoint cycles. I know from the first lemma that we proved today, the first theorem, I don't remember if I called it a theorem or a lemma. The first theorem that we proved, that the order of a cycle is its length. So the order of sigma 1 is L1 and the order of sigma 2 is L2. And then the other theorem we proved, lemma we proved, was that if I have 2 disjoint things, then I take their least common multiple to get the order. So I just take the least common multiple of L1 and L2. So now we prove the induction case. The induction case is when I assume that I have it for k minus 1 and I want to prove it for k. So assume the theorem for k minus 1. If sigma 1 through sigma k are cycles of length L1 through Lk respectively, what happens if I start, what structure do I want to put on this? Because I want to use the previous lemma again. Sigma 1 up through sigma k is sigma 1 up through sigma k minus 1 times sigma k. Right? I can regroup how I want. That's what the associativity property tells me. I can move my parentheses around. So I group these together, and I call this permutation pi. So this is pi of sigma k. Now these cycles are all pairwise disjoint. So once something is fixed by pi, once something is moved by pi, it has to be fixed by sigma k, because it has to be moved by one of these, exactly one of these. And once something is moved by sigma k, it has to be fixed by pi, because once it's moved by sigma k, it's fixed by all of the cycles sigma 1 up to sigma k minus 1. So these are disjoint permutations. So by the previous theorem, our lemma 4.2.5, the order of sigma 1 up to sigma k, which is just pi sigma, is the least common multiple of the order of pi, this is k, and lk. But the order of pi by induction is this least common multiple of L1 up through Lk minus 1. So the order of sigma 1 up to sigma k is the least common multiple of L1 through Lk minus 1. And then I take a least common multiple of this thing with Lk, which just turns out to be exactly what you want it to be. The least common multiple of L1 up through Lk. Because the least common multiple of these two things has to be divisible by L1 up through Lk and Lk itself as well. So it's not difficult to see that these two things are the same. And that's the end of the proof, right? This is often a feature of induction proofs, or proofs when you want to build things up one at a time, right? So I prove that I can tack one thing on at the end, no matter how complicated the cycle pi and sigma are, as long as they're disjoint permutations. Notice here that this is not cycle, this is permutation. So as long as pi and sigma are disjoint permutations, I can find a way to compute what happens when I take their product. So here, I just sort of tack them on one at a time, and I see that I keep getting a least common multiple. That's basically this inductive proof, how it works. Okay, so the last thing I want to do today is just go over some examples of computing or seeing sort of this theorem in action. So what are some examples? So let's do something silly. In S5, the order of 1, 2, and 3, 4, 5 is, it should be 6, right? Because the least common multiple of 2, which is the length of this cycle, and 3, 4, 5, which is the length of this cycle, is, and 3, right? So 2 and 3, least common multiple is 6. So let's just check it. Sigma squared. Well, I swapped the roles of 1 and 2, so this just becomes the identity. If I take sigma squared, 3 goes to 4 goes to 5, so this is just 3 goes to 5. 5 goes to 3 goes to 4, so 5 goes to 4. And 4 has 4 goes to 5 goes to 3, right? Because I'm applying the permutation twice. So this is sigma squared. Sigma cubed. Well, where does 1 go if I apply sigma squared and then sigma? If I apply sigma squared, 1 is fixed, and then if I apply sigma, 1 goes to 2. And similarly for 2, if I apply sigma squared and then sigma to 2, 2 is fixed by sigma squared, and then it's sent to 1 by sigma. What happens if I do 3, right? So I plug 3 into here. I want to see what happens when I apply plug 3 into sigma squared of sigma of sigma squared, rather. So 3 plugged into here goes to 5, and then I plug it into here, 5 goes to 3. So the 3 is fixed. 4, if I plug it into here, goes to 3, and then 3 goes to 4. So 4 is also fixed. And as you might guess, 5 must be fixed. 5 goes to 4, 4 goes to 5. So sigma cubed is just the 1, 2. Sigma to the 4th, well, sigma to the 4th is, where does 1 go? Well, 1, I need to do sigma of sigma cubed, right? So if I want to see where 1 goes, I plug 1 into sigma cubed, it goes to 2. And then I plug it into sigma, it goes back to 1. So 1 is fixed. Similarly, 2 is fixed. 2 goes to 1, 1 goes to 2. And then 3, 4, 5 is going to do its thing under sigma, right? Because 3, 4, and 5 are all fixed by sigma cubed. So when I plug it into sigma, 3 goes to 4, 4 goes to 5, 5 goes to 3. So I just get 3, 4, 5. Okay, and finally we'll do sigma to the 5th. So again, 1 is, nothing happens here when I apply sigma to the 4th. So I apply sigma, 1 goes to 2, and 2 goes to 1. But 3 goes to 4, and 4 goes to 5. So 3 goes to 5, 5 goes to 4. Let's you check that. And now you can see that these two cycles are inverses. These two cycles are inverses of one another. So sigma to the 6th is indeed equal to the identity. So this is an example of computing the powers of a cycle to find its order. Or you can, once you know its cycle decomposition, you can find the order much more simply just by taking the length of these cycles and then taking the least common multiple. Let's do one more. In S6, the order, actually, let's do S12. So 1, 2, 3, 4, 6, 7, 8, 9, 10, 11. It should be an order 12 element again. Right? Because here the length of my cycle is 4. And here the length of my cycle is 6. So here I just multiplied. Here the least common multiple of 4 and 6 is 12. So this example, I'm not going to compute this one, but it shows something important. And that's the order does not determine the cycle structure, right? Because you may be tempted to think that. But here, this is an order 12 element, but the cycle of length 12 is also order 12. So two elements can have the same order but different cycle structures, right? This is a length 4 cycle times the length 6 cycle that are disjoint, and this is just one big length 12 cycle. Okay, so we're already at 45 minutes. I was going to talk a bit about the other topic for the next topic in the section, which is the sign of a permutation, but we'll save that for Wednesday. So I hope you all are doing well. Please, please, please do not hesitate to email me if you have questions about the homework, the project, anything. And I will talk to you soon. Have a great day.